brings us to the high-mass stars. They have the most interesting deaths. In high-mass stars, things don't stop with the formation of carbon in the fusion chain. Other thermonuclear reactions can take place to make even more complicated atoms. Among the important reactions are carbon going into oxygen and oxygen turning into silicon. These reactions take place much more quickly the larger the atoms. Many of the most common elements heavier than hydrogen and helium are formed this way. The insides of high-mass supergiant stars are the only places we know of in the universe where these atoms can be made in substantial quantities. Later in the course, we're going to learn that when the universe was formed, it first contained only hydrogen. Helium was formed in the first few minutes of the universe, but only a negligible quantity of any other element was formed at that time. The carbon that our bodies are made out of and the oxygen that we breathe were all made inside stars that existed before the solar system was formed. These atoms were blown out into space from the stars and collected again to make a new cloud that formed our solar system. We can tell which elements can be formed inside red giant stars by looking at the physics of nuclear fusion. Now this graph shows how much energy is contained in atoms of different atomic numbers. If we move down the graph, energy is given out. So therefore, we get energy when we go from hydrogen to helium, and from helium down to carbon, and all the other elements. But if you go to an element of mass 80 to an element of mass, say, 40, we need energy, so we can't do that. It takes energy put into the system to do that. Therefore, we can make all the elements simpler than iron in the center of a red giant star, but nothing more complicated on this side. There's a curious relationship between the radius and the mass of a white dwarf star. The more mass it has, the smaller it is. When it gets to a mass of 1.4 solar masses, the white dwarf has 0 radius, which effectively says it can't be a white dwarf anymore. If I were to plot, this is the radius over the radius of the Sun, and as we get down here and we look at its mass, when we get down to 1.4, the radius goes to 0. That limit is called the Chandrasekhar limit. If the core of a star tries to form a white dwarf with a mass greater than this limit, it keeps collapsing to ever smaller sizes, giving off enormous amounts of energy. Because of Newton's law of gravitation, the smaller something gets, the more energy it gives out. So the collapse of the core of a high-mass star gives rise to a supernova, which is an extremely powerful explosion of a star when its core collapses. The star brightens by millions of times in a few hours with no warning to astronomers. This only happens in our galaxy a few times a century and usually in a place we can't see it. There was one in the Magellanic Clouds, which is the nearest small galaxy to the Milky Way galaxy, in 1987. The light from a supernova fades over a period of a year or so. Now, 3 major things happen in a supernova. The outer layers of a star get blown out into space to form a nebula. The Crab Nebula is one of the most famous of these. It's a result of a supernova explosion that was seen by Chinese astronomers in the year 1054. It's a slowly expanding nova, and it gives off powerful radio waves and X-rays as well. The gas spreads out into space and eventually fades away. Here's a picture of the Crab Nebula. It's essentially just an explosion of gas from this star. Now there's lots of different supernovas. This is another remnant of a supernova called Tycho's remnant, and it's seen in the radio frequency. And this is Cygnus Loop, which is another supernova explosion. Now, so much energy is available from the collapse of the core of a star that for a brief period, measured in thousandths of a second, nuclear reactions can take place that form elements heavier than iron. Elements like gold, silver, lead, iodine, uranium were all formed in the few thousandths of a second during a supernova explosion and blown out into space. All gold comes from a supernova explosion. The core of the star collapses and forms a neutron star, which we'll discuss in just a few minutes. Supernovae are so bright that there are records of supernovas going back thousands of years. These records are very useful to scientists because we can sometimes identify a supernova remnant that is now seen only by radio telescopes with an actual supernova explosion that took place a long time ago. Some of the descriptions of how the light faded are good enough for us to be able to estimate what type of star caused the explosion. The oldest records are from China and Korea. Neutron stars are much smaller than white dwarfs. A typical neutron star is about 6 to 10 miles across, with a mass of several times that of the Sun. The density of a neutron star is 10 to the 8th tons per cubic centimeter. A neutron star is one possible end state of a supernova explosion. Now, it was theoretically derived in the 30s by Walter Bade and Fritz Zwicky, and a neutron star has the following properties: a radius of about 10 kilometers, a mass between 1 solar mass and a maximum of 2 to 3 solar masses. Because of its small size, neutron stars were thought to be unobservable. The material of a neutron star is similar to the nucleus of an atom. A way of understanding the neutron star is to think of gravity being so strong as to collapse the atoms themselves so that their nuclei combine. They were predicted theoretically in the 30s based on calculations using quantum mechanics. Again, it was originally believed that they were unobservable because of their small size. However, in 1967, another stellar object called a pulsar was discovered. And there's sources of intense radio emission that flash on and off with periods of a few seconds down to a few fractions of a second. A small number are also visible pulsars. Pulsars flash for the same reason a lighthouse flashes. The radio waves are produced in a region of magnetic field that surrounds the neutron star. The fast rotation is another example of the law of conservation of angular momentum. If the Sun, which we know rotates about once a month, collapsed to the size of a neutron star, it would be spinning at a small fraction of a second. The ultimate fate of a neutron star is to slow down and fade away. Now, ordinary pulsing variables obey a period density relationship, where the period is inversely proportional to the square root of its density. The long periods of the first pulsars were discovered were consistent with them being white dwarfs. Later pulsar discoveries had much shorter periods. The theoretical neutron star was dusted off for consideration, although at first it appeared that neutron stars would pulsate too fast. The key to explaining pulsars turned out to be a rotating neutron star, not a pulsating one. By conservation of angular momentum, an object as big as the Sun with a 1-month rotation period would rotate more than 1,000 times a second if squeezed down to the size of a neutron star. Such a size reduction is exactly what is expected of a collapsing massive star's iron core. A collapsing massive star is expected to retain its magnetic field, endowing the neutron star with an extremely powerful magnetic field. The powerful magnetic field is such that it beams radiation energy in 2 opposing directions. The beamed radiation together with the rapid spin gives the pulsar its observed characteristics. Like dynamos on Earth, the spin of the neutron star's magnetic field, not necessarily aligned with the physical spin axis, creates an electric field. This electric field is intense and rips particles from the surface and channels them into 2 narrow beams at the magnetic poles. The charged particles then accelerate to speeds close to that of light, and in doing so produce radio emissions along the polar axes. Visible light and gamma rays may be produced in very young pulsars. Radiation produced in this manner is called non-thermal radiation, or synchrotron radiation. Then the pulsation of a pulsar is a result of one of the radio beams sweeping across the Earth. Just like a lighthouse, the light is always going as it comes around. You only see it on a ship as it goes around. A pulsar is sending material out, but we only see it as it rotates around and the beam is pointing towards Earth. Electric and magnetic fields of a rotating pulsar exert forces on charged particles in its vicinity and speed them up. The charged particles in turn exert a reaction force on the neutron star, so consequently, if the neutron is forcing them out, the neutron stars should slow down with age, and that's exactly what is observed.